So in this lecture, we're going to talk about how to solve Michaelis-Menten problems. And specifically, we're going to discuss what assumptions we need to make and some observations that come out of looking at these equations that allow us to reduce the number of equations down to a couple of manageable forms. So first off, just recall that we have a substrate binding with an enzyme to form a complex. That complex then produces a product at a given chemical rate, and then releases the enzyme back into the media. And so for each one of these quantities, S, E, C, and P, we have a differential equation that measures the rate of change of those concentrations. So the rate of change is commonly measured of as being rate in minus rate out. So here's rate in, there's rate out for this first equation. The rate in is our C that's breaking back down into our substrate plus enzyme. So that happens at a rate of K to the minus 1. And then we have S being used up. The rate at which that concentration is going out is by its reaction with the enzyme. It's binding with the enzyme, and that we assume is some sort of mass action. So it's proportional to how much concentration of S there is times how much concentration of E there is. We can make that argument for all four of the equations. Notice one correction here is that this last term on the second equation should be concentration of C right there. So let's see what we can do with these equations. Notice that if we add the second and third equation together, so we take these two and add them together, the negative and the positive mass action term cancels. These two cancel, the net middle terms cancel, the last terms cancel. So the sum of the middle two terms is 0, which means that the derivative is 0, and the only way a derivative is 0 is if the function is constant. So E plus C is some constant. And we'll call that E0. So E0 is the total amount of enzyme that's either in the free or bound position. And it's conserved during the reaction because the enzyme is only a catalyst. So this is the total amount of enzyme in either the free state E, so in state E, or bound with in our complex C. And throughout this reaction, it's going to stay constant. It's just catalyzing the reaction. It's not really going to be used up. Notice if, in addition, if we add together the first, second, and last equations, the right-hand sides also cancel. So we get the mass action terms going away. This K1C goes away with one of these, and then the K2Cs cancel off there. So that also gives us 0, therefore implying that S plus C plus P is also constant, and we'll call that S0. So this is S0 is the substrate that occurs in the original form S, bound to the enzyme C, or as converted into the product P. So we're assuming that in either one of those forms, that sum does not change throughout this reaction. So original form, bound to the enzyme, and then converted into the product. So with these observations, our equations can be reduced quite a bit. So let me clear off if I can. And apparently I can't. Let's see if I can. Oh well. So let's take these equations and see if we can reduce it a bit. So I'll go up here, and let's see. So the first equation, the ds dt, can be written as K minus 1 of C. So that hasn't changed. It's still this term right here that I'm circling at the top. But then minus K1, and now instead of using E in our mass action term, we're going to use the fact that from our first observation, E is the same thing as E naught minus C. So that simplifies that equation quite a bit. And we'll do a similar thing for the equation for the concentrate C. That's going to be negative, C is positive K1 S times E. Instead of E, we're going to use our E0 minus C, and then minus, and I'm going to combine these two terms together. So this was originally K minus 1 C minus K2 C. I'm going to factor out the negative, and so this is K minus 1 plus K2 times the concentration C. So we have only two equations using the fact that we can solve these two equations for S's and C's, right? That's the only thing that these equations involve is concentrations of S's and C's. And once we know S and C, then we can find from that information what E is, because it'll be our total amount of enzymes minus C. And once we know S and C, then we can find how much concentration of product we have, because that's going to be our total amount of substrate minus S and minus C. So once we solve our equations, our two equations, we get the other two quantities for free. So let's look at a specific example. So this example, we consider a problem in which urea combined with water results in ammonium carbonate, so smelling salts. To achieve a sufficiently fast reaction, we assume that this enzyme urease is necessary. So we have this idea that this enzyme comes in, speeds up this reaction, and acts as a catalyzer. So the formula for it, you commonly see in a chemistry textbook, looks like this. So the idea to take from this is that our substrate is urea, our enzyme is urease, so E. Combine those two together, that's our complex, so we'll use UE, and then A is our product. So in terms of what we saw earlier, this is acting like our S, our E, C, and P. So the equation involves two parts. First, the combination of urea and urease to form this product, and that product can be broken back down at a given rate K minus 1. And then this product, when it gets water added to it, becomes, so when this complex gets water added to it, it becomes this product, and then the enzyme is released. So let's see if we can set up some equations for that reaction, and then we'll try to reduce it using the observations we did in the previous slide. So our equations are going to be for the amount of substrate, so our amount of urea. Let me make that a little bit cleaner looking. It's a little messy. So du dt. And we're going to have another equation for the amount of enzyme. And an equation for our complex, UE. And then finally an equation for the product, which we're calling A. So U gets used up by interaction with the chemical reaction with U with its enzyme, and we are actually given that rate. So I'm going to replace that K with our definition here. Suppose that's 3.01, and then times the amount of substrate present, urea, times the enzyme being used. So there's our mass action being relating this left side to the right side, and then that's decomposed back in from our complex at a rate K minus 1, which is 0.02, so a much slower reaction. And that is just depending on how much complex there is. And let's see, any other U's? Nope, no other U's. So that's the only equation we have. For E, we have it being used up in our reaction. So it's binding with this complex. We also have it broken back down. But then also we have it being released after the complex is combined with water, and that's released at plus K2, so 0.1 times how much UE there is, so how much. The reason I paused there, I think these all should be moles per second. And then for our product, we have, or it's not a product, but our complex, we have that being positive 3.01, the combination of U and E. And then that's getting used up, K2 UE. And then finally A, our result comes in at K2, oh, sorry, I should use K2 being 0.01. So let me erase that. So let's see, 0.1, and then that becomes our 0.1 UE. And I think I'm missing one other thing. Let's see, we have 0.2, so we have the backwards reaction, we're losing our complex, sorry, I forgot about that one. That's the K minus 1, so 0.02 times how much UE there is. So we lose UE in two directions, one where it goes back into our, or degenerates back into our urease plus our enzyme, and then one where we use it up with our water to create our product. So now notice what ends up happening with these equations when we have some initial information. So on the next slide, let's talk about that. At time equals 0, suppose we know what the amount of substrate, enzyme, complex, and product are. Then we can make some simplifying reductions to our equations, because from 2 slides ago we said that the amount of enzyme in both forms, the free and the bound, should equal a constant, E0. Now for us, this is E plus RC is what we call UE, the urease. And so this would be that because we know initially we have 0.2 moles of enzyme, now urease is 0, E0 will be 0.02. So wherever we see E in our formula, that's going to be 0.002 minus UE, amount of complex. Similar to that, we said that if we had our substrate plus the substrate bound to our enzyme, so that's our complex, plus the converted substrate or product, that also was constant. And so initially, we have 0.1 moles of substrate, no complex, no product, and so that's S0. So our product can be thought of as being 0.1 minus S minus UE. And S here would be our U. I should make that U. So our equations reduce quite a bit, and let me see if I can fit it in here. They become d dt of our substrate U equals negative 3.01 U times E0, which was what we know, that was our 0.02, minus UE, and then plus 0.02 UE. That should be UE. And similar, our equation for the amount of a complex, UE, is positive 3.01 U times 0.02 minus UE, and then minus the sum of our two reactions, 0.02 plus 0.1 UE. So we have two differential equations for U and E, and then once we know what U and E are, we can use this formula to figure out what the amount of enzymes is, and once we know what U and UE are, we can find our amount of product. And these equations are sufficiently hard that we can't try to solve them by hand. Instead, we rely on a computer to solve it. And so here I've graphed the solution with a program called Mathematica to help us out. So we have 4 graphs. Each one represents the graph of the substrate U, the urea, the enzyme, our A, which is our product, and the complex UE. So which one's which? Well, we can kind of see a little bit what's going to go on, because at time equals 0, this is time equals 0, then we can see that at 0.01, that must be our amount of substrate. And so hopefully it makes sense that during this chemical reaction, the substrate gets used up. It declines down to, oh, that's not the arrow I wanted. Okay, here we go. It goes down to 0. There we go. It goes down towards 0. So it's getting used up. The 0.02 is the original amount of enzyme. So this right here, which means this graph right here that corresponds to it, is our enzyme. Now hopefully that makes sense too, because initially it's a catalyst. So it starts our reaction off, it gets used up, but then as our substrate gets bound into our complex and we produce this product, the enzyme is freed up again and returns back to its initial value. So you can see that it gets used up and gets returned back to its usual value at the end of our reaction. And then our other two graphs, well, one is going to be the complex, and that's what happens with our enzyme. It's going to go up briefly, and then once the complex breaks down into our product, or at least our enzyme, it's going to go away. So that's our middle sort of step of our complex. So this bottom one is UE. And then the last graph is the graph of our product, which increases as our chemical reaction goes. And notice it eventually levels off, right? So at some point we're going to run out of substrate to bind with our enzyme, and there's going to be no product left to be converted or to be made, and so we expect the concentration of the product to level off, which it does. So these equations that describe the chemical reaction do a pretty good job of capturing the dynamics of this chemical reaction.